As we've seen, it was the introduction of sophisticated material handling systems like these very narrow aisle or V&A lift trucks that first created a demand for flatter and more level floors. That was in the 1970s. It was quickly recognized that the efficient operation of these trucks depended on extraordinarily flat and level floors. Years later, these pictures were taken to illustrate the point. They show the same truck operating on the same floor before and after the floor was ground from conventional flatness to super flat tolerances. The need for flatter and more level floors was obvious. How to get them, that was complicated. To make concrete floors flatter, you first had to figure out a way to describe and measure floor flatness. As we've seen, the old straight-edge specs weren't really helpful, so a new system had to be developed. The goal was not only to control the envelope, but also to control the floor's bumpiness. Or if you look at the floor profile as a wave, you need to control both its amplitude and its frequency. Over several years, the face companies developed a system to combine both properties into one number. They called it an F number. The first measuring device built to work with F numbers was the face floor profilograph. The profilograph is a vehicle simulator. Its wheels are set up just like those of the lift truck will be when it operates on the floor. Since V&A trucks are wire or rail guided within the aisleways, they always travel in the same wheel paths that are set from the time the building's racking system is designed. So if the profilograph is set up in those same paths, it will feel the floor profile just like the truck will when operations begin. The profilograph draws the floor's profile on a paper tape. The pen traces on the tape determine the F number. If the profilograph were measuring an average conventional floor, it would produce a graph that would look something like this. In terms of F numbers, an average conventional floor is about an F20. The term superflat is used to describe floors which measure F100 or better, the flatness required to support V&A operations. That's about 5 times flatter than an average conventional floor, so on a superflat slab, the profilograph readout would look something like this. Since the invention of the profilograph, it's been possible to match various design techniques and construction methods with the flatness and levelness they produce. This led to better and better results in the field, and since 1980, 3 North American contractors have actually produced floors which measure F200 or better. That's twice the flatness of superflat, and 10 times flatter and more level than an average slab. That means that from one wheel track to another, the difference in elevation anywhere on the F200 aisleway is about a 32nd of an inch, or half the thickness of a quarter. But the floor flatness problem was far from solved. The original F number system worked only in the tiny percentage of buildings where the traffic was restrained by wire or rail guidance. These slabs became known as defined traffic floors. But in 99% of commercial and industrial buildings, traffic patterns are not restricted. Vehicles and pedestrians might travel any one of an infinite number of possible paths across the floor. This kind of floor is called a random traffic floor, and since the profilograph obviously could not measure every possible path, a second system of measurement was required. By late in 1988, the American Concrete Institute had completed its work on an F number system for random traffic floors. This system based on 2 F numbers, FF for flatness and FL for levelness. All jobs would be specified using one FF value and one FL value, such as FF35, FL25. All F numbers would be based on a series of measurements of the floor's elevation. Measurements would be taken every 1 foot. The elevation points would be analyzed at 2-foot intervals to determine FF and at 10-foot intervals to determine FL. One way to measure F numbers is with the dipstick floor profiler. This model automatically records the elevation readings for computer analysis. Another version requires the operator to record the data orally on an audio tape recorder or on paper for later manual entry into a computer for F number analysis.